Okay, in this video, we'll be going over buffer concepts and what a buffer does and the purpose of a buffer. So first of all, a buffer is created when buffers are created when you have a acid-base conjugate, acid-base conjugate pair in significant amounts. So this may sound familiar because this is actually the common ion effect. So when you have an acid-base conjugate in significant amounts, then you're going to have H. So you'll have HA, HA being the weak acid, and you'll have like Na, A. So and so the Na like are like a group one spectator. So this basically does nothing. So really what you have is like A minus. So this is a weak acid, and this is its conjugate base. And as we saw, if you have both in significant amounts, so let's write a dissociation equation for this. As we saw in the common ion effect tutorial, that if you have some number here and you have some number here, then you're going to have not as much will go to the right. So what that means is it actually resists pH change because not as much of this will make protons if something is there. The other aspect of a buffer that's important is, so that's what a buffer is, and here's why it's important is when you have the conjugate pair present, then the buffer can consume it can consume a strong acid or a strong base. For example, let's say you have a solution of 0.100 moles of HF, for example. Okay, and then this is added to a beaker. Okay, also you have 0.100 moles of NaF, which, as we know, the Na doesn't do anything, so really what you have is 0.100 moles of F minus. So this is also in the solution. So you have the acid-base conjugate pair. Now let's say you decide to add a strong acid, so HCl is added. So this is a strong acid. And if we identify what else is in there, this is a weak acid, and F minus is a weak base. It's the conjugate of a weak acid, which is a weak base. So we have a strong acid, a weak acid, and a weak base all present. So, and as we know, this dissociates, so you're going to have H plus and some Cl minus. And as we know, this doesn't do anything. Okay, nor does the sodium, nor do the sodium ions. So we'll write them out, but I'll cross it out to indicate that it doesn't do anything. So here you have a strong acid, a weak acid, and a weak base. So the question is, what's going to happen? Will there be an interaction between two of these? So a weak acid and strong acid are not going to interact, but a strong acid, here you have an acid and a base, so there should be a reaction between this and this, and in fact there is. So if you had a question that said, and let's say you had a zero point 0.1 mole, or actually let's say you have 0.050 moles of the strong acid. So you're going to have an interaction between the strong acid and the weak base. So depending on what you're starting with, your entire mixture, that's going to dictate the rest of the problem. So this is the key feature of a buffer problem, is you have to read the problem carefully, and the very first thing to always do is identify exactly what you have in the solution. So by either calling it a weak acid, strong acid, or weak base, or a strong base. So um, So let's go ahead and carry out this problem. Um, and just because this is more a conceptual tutorial, I'm going to deal with the problem solving on the next tutorial, and I just kind of want to go over the concepts of what's going to happen in this mixture. So it's kind of like this ion, it's like this ion stew where you have like there's like steak, potatoes, carrots, um, peas, onions, whatever. Okay, and so you have to figure out like which two, if at all, are going to interact. So in this case, our reaction, we're going to have a full-blown chemical reaction between the strong acid and the weak base. So those two we need to deal with in an earth table. So we'll set it up like this: H plus plus F minus, and the product of this is going to be HF, which lo and behold is actually the conjugate of F minus. So there's more to do after we solve this little problem. Technically, I'll write over here on the side just for teaching purposes. I'll draw a squiggly line. Remember that our H plus is actually H3O. So our strong acid immediately will react with water and make H3O in a one-to-one relationship. So another way to write this chemical reaction is to write it like this. So we have an acid and a base. This always makes water. So we'll have HF and H2O will be the other product. So remember that this reaction is the same exact thing as this reaction. Okay, but just to simplify things, I'm not going to show water in our reaction. So we set up an earth table, and remember in earth tables we work with moles. And we're so used to doing ice tables right now. And remember, with ice tables, you're working with molarity, or if they're gases, sometimes you might use pressures, atmospheres. So remember, in earth tables, we want to work with moles here, um, or or grams, but moles is of course always easier. So H plus we had 0.050 moles, and our F minus we had over here we have 0.10 moles. And HF is not 0. There's actually something there. So HF, there's 0.1. So we're going to put that number here. So we write 0.100 moles here. And the great thing about most of these buffer problems is everything is happening in a one-to-one relationship. So it's easy to tell which one's going to run out, which one is limiting. So the one that runs out is going to be the H plus. So because this is they're reacting in a one-to-one ratio, and you have less of it. So this is going to be minus 0.050. Let me get rid of that squiggly line. Minus 0.050. Of course, our reactants decrease over time, and our products are, of course, increasing over time. So this will be plus 0.050 on an earth table. So this is 0. This will be 0.050, and this would be 0.150 moles. Okay, at this point, we need to again assess what we have in our mixture. So we notice what the buffer did. Our buffer consumed. So because we had this present, our buffer consumed the strong acid. So it's a 0 now on the F line. So it fully consumed it, and you'll see that it's going to resist pH change. So you had, if before this was added, let's back up a little. So before this was added, we had a certain pH. Okay, it happens to be, if our conjugate is equal in amounts, it happens to be equal to the pKa. But we have a certain pH going on here, and then we decided to add a strong acid. So we'll see that because we added the strong acid, it will consume the F minus, but you'll see the pH doesn't change by a whole lot. So let's actually end our tutorial here, and we'll just kind of leave one final note about buffers is the buffer So the conjugate pair will eat up any strong acid or strong base present, which will ultimately result in not much of a pH change. Okay, and we'll work through some problems when we go over our buffer design tutorial. So how to like design a buffer, and we'll go over a problem or two that shows how that works. Okay, so for now, that's the end of this tutorial.